Hey everybody, welcome to Question Barn. This is the fourth Question Barn episode. You know, it's just me and one of my titanium physicists, and we answer one of your questions. You want to send us a question, it's TIPHYTER, TIE Fighter, at titaniumphysics.com. Today joining me, it's Ken Clark. Hey, Ken.
Hey, Ben.
How you doing?
I'm doing quite well. You?
Yeah, I'm great. It's time for the segment of the show where we talk about our lives. What's new with you, Ken?
Let's see. What's new? Finished teaching courses for the term, which is good. I'm glad to have that over with. I'll be doing some traveling coming up. That's about it.
Oh, really? Where are you going to go?
I'm supposed to go to Fermilab on Thursday, and then I'm heading to the Niels Bohr Institute in Copenhagen for a week next week.
Wow. That sounds great.
Yeah, it should be fun.
Yeah, I mean, life for me is just, our term is just finished, so we'll wrap everything up and then get the train ready to turn around, and then more teaching in January.
Yep, never ends.
Yep. Actually, I'm in the middle of editing the next episode of Titanium Physicist. We recorded it in mid-November, actually, but it's just this sprawling topic. We talked about CPT violation, the topic, and with the guy who made the Over the Garden Wall cartoon. I don't know if you've seen that.
Oh yeah.
And it's a good episode, but it's long. It's about 2 hours of audio that I'm wading through, and I'm so embarrassed because it's just me over and over being stupid. So it's taking forever to edit.
That is going to take a while.
Yeah. There's a lot of stupid there. So yeah. I mean, people are like, "Hey, where's the next episode?" I'm like, "I don't know." and then we're gonna record another Question Barn before I put that one out about Interstellar. Have you seen Interstellar yet?
Haven't.
Oh, it's good. It's really good.
It actually kind of started a big fight in one of my classes about whether it was great or whether the scientific directors had really dropped the ball on space travel.
Why? Okay. Why? What was the problem?
I haven't seen it, but half of the students, or roughly half of them, thought that their depiction of space travel was ridiculous.
Yeah, a little bit. Well, okay, so it becomes a science. It starts out as kind of a really, really hard science fiction movie when they're like, okay, so there's this wormhole out by Saturn. We got to go through this wormhole. So they get in a spaceship. They take their rocket up to the spaceship, and then it takes 2 years for them to get out to Saturn. Right? They have to do some gravitational slingshotting to get there.
Okay,
as you would.
It
was okay
so far.
And then they go through the wormhole, and they have to visit a sequence or a series of planets that might be habitable. And they do it all in this rinky-dink spaceship. I mean, it's smaller than a rocket, and they essentially it's like a shuttlecraft from Star Trek, and
Nice.
They take off and land from the planets, and they visit several planets in the course of a few months in their time. You know, they're like, oh, we'll go out to this other planet, and it's like you took 2 years, and including gravitational slingshotting to get to Saturn, and now you're piddling around in different these planets aren't that close to each other. What are you guys doing?
And where did the wormhole come from?
Yeah, well, okay, so there's something interesting in the show. We'll talk to about more in the thing, right. But I mean, it's the deal is that. Well, okay, we'll do it in the next one where I can spoiler it. I'll tell you after the show if you really want to know.
Just say it's Deus Ex Wormholenia.
But it's not. It's a self-consistent part of the plot. It's a very clever use of general relativity.
Okay.
Yeah. No, I really like it. The movie made me cry because it was so pretty.
Wow.
Yeah, I know. Nothing makes me cry. Once I was around you, actually, we went and saw a kung fu movie that shut me up for 20 minutes afterwards. But
no crying.
But no crying. Nothing makes me cry. You can hit me with a hammer and I'll just whine. I whine a lot, but I rarely ever cry.
I can vouch for that.
All right, so let's deal with today's question. This is from a guy named Ralph. I'll read the email. He goes, "Howdy. The Higgs boson turned out to be a massive particle, from what I understand. It is also supposed to be a field through which everything moves. So there must be a lot of them, I reason. So could this be the missing mass of the universe? Maybe there is some obvious reason that it's not, but I haven't heard the idea mentioned, and it seems obvious to me." All right. So the question's kind of like, hey, are Higgs bosons dark matter? I think is the summary. What do you think, Ken?
I think it's a great question. I mean, basically he's saying, we now found the Higgs. It's got some mass. There's a whole load of them out there. So is this it? Is this what we're missing?
Yeah. What do you think?
And I think that's a good question. It's not, but it's because of some really interesting ways in the way that mass is imparted, essentially. And I think that's pretty cool. So, good question.
Yeah. Okay, well, let's break this down a little bit. So first off, it's not. We know that the Higgs bosons aren't dark matter. For one thing, they're unstable, right?
Yes.
We detected the Higgs boson not because we have a Higgs boson detector, but because one was created, or several were created. They get created in CERN, and then they immediately explode into a shower of other particles.
That's right. And we see that they existed because there is this what's called a resonance, essentially. There's a whole bunch of stuff that their mass adds up to what it came from, which is the Higgs in this case. Right.
So we look at the exploding stuff on the street and we say that was once a Higgs boson. There's a consistent amount of mass that goes into making a Higgs boson. We know that, at one point in time, all of this matter turned into a Higgs boson and that exploded.
Mass and energy. I'll correct myself there because that's going to become important later.
Sure. So the moral of the story is, these things don't stick around.
Yeah.
But how does the Higgs? So what we say when people say the Higgs boson is the thing that makes mass, what they mean is that matter couples to the Higgs field. There's something called the Higgs field around it. It's the same way there's an electromagnetic field, or a magnetic field, or a gravitational field around us. There's a Higgs field around us, and it's matter coupling to the Higgs field that generates mass, right?
Exactly, and it's an interesting way that you have to define mass. I mean, essentially, what mass means in this case is that particles are resistant to being accelerated, right?
Right. So
that's the way that we define mass in this context, in the way that this is being discussed.
Yeah, there's people. So the biggest sin of all, I think, was the lousy analogy that said that Higgs boson gives mass the way a whole bunch of people in a room around a celebrity gives that celebrity mass as he tries to move, because it kind of gives the impression that it's Higgs boson sticking to you that gives you mass. But it's really kind of, well, here's an analogy. Let's suppose we talk about mass in terms of how hard it is to accelerate. Imagine this Higgs field is like a carpet, and your mass, it depends on how much you couple to this field. So it depends how much Velcro there is on your shoes. So some people with lots of Velcro on their shoes, they're going to stick to the carpet, and they're going to have to drag the carpet along with them anytime they want to accelerate in any direction. And so that additional drag on you as you try to move around is effectively what we see as mass. Is that an okay analogy? Is that dumb?
No, I think I've heard kind of the one before where you're trying to roll something like a ball bearing across a floor. And like if it has, very little mass, it's like a hardwood floor. But, as you increase the plushness of the carpet, essentially you're giving it more and more mass, right? You're making it more resistant to acceleration.
Mm-hmm. So that's, I don't know. Is there anything else to say about this, do you think?
About the question? There's tons of other things to say about it.
What else you got, Ken?
Because I think it goes back to the reason that we know dark matter exists. Mm-hmm. And we know dark matter exists because we see all this evidence that there's something out there in the universe that is essentially, it has some kind of mass. I'm going to use the same word because we don't have a better one. It has some mass, and it's causing things to divert, like it's causing things to spin in a different way than we thought they should, et cetera, right?
Yeah, it's galaxies. And, well, yeah.
Exactly. But the kind of disconnect comes in the way that we talk about it. So that's gravitational. But gravity, and this is, going into your field,
right.
Gravity couples to mass and energy, a combination of mass and energy, right? Whereas the Higgs essentially gives things just the mass, and it only gives it to fundamental particles. So it's a very different situation. It looks like there's a connection between the two, but there's only a very weak connection between the Higgs field and gravity.
So you're saying that, hold on. You're saying that, well, okay, let's try this.
Yeah, it gets complicated here, which I think is why it's a great question.
Yeah. So what you're saying is that it's not the mass of the Higgs that's necessarily causing all of gravity. Is that what you're saying?
Yes, exactly.
Right.
So the Higgs only gives mass to fundamental particles, and it only couples to the particles themselves, not, for example, the energy that they have, their momentum or their other energy.
Right. Yeah. So the Higgs coupling to the Higgs field is kind of like it's like a type of potential energy. I said back when we recorded an episode on this that it's kind of like compressing a spring. I try to refer as little as possible to E is equal to mc squared, but this is really where it comes in. The idea that anytime there's a potential energy of the system, that can translate into mass. So if you had a spring on your desk and you compressed it down so it was like flat and super squished up, then that compressed spring would have just a little bit more mass. It would be a little bit harder to accelerate than if it was a normal springy spring expanded out. That difference in potential energy is what makes it hard to accelerate.
That's right.
And we see mass showing up in particle physics for different reasons. Like you take if you take a neutron and you can let it decay, you can make a neutron by smushing together a neutrino and an electron and a proton, right?
Yes.
But there's a little bit less mass in the neutron. There's a little bit more mass in the neutron than there is in the mass of its constituent particles.
It takes you effort to get it together.
Yeah, it takes you effort, and that's like squeezing the spring, and that's why this fast that you have to kind of compress the system down. You're pushing against something to build the system means that the overall rest mass of the neutron is going to be heavier than the rest mass of the constituent particles.
Yes, that's right. And I mean, and importantly, the Higgs doesn't couple to the neutron, right? It couples to the quarks in the neutron.
Right. Yeah. So there's nothing Higgsy about the difference in mass between the two. It's all just E equals mc squared. There's a difference in potential energy between the two. And that's why one is heavier than the other.
And so when we think of, one way to think of it would be you have a bunch of quarks, well, 3, that make up a neutron, and inside their little cage, they're spinning around furiously, right? Mm-hmm. And gravity couples to the fact that they're there and that they're spinning around. But the Higgs only couples to the quarks themselves, and that's a small portion generally of the actual, what we would call the mass, the gravitational mass.
Right. So the overall gravitational mass and the inertial mass are the same thing. But yeah, effectively, what couples to gravity? Gravity isn't coupling to the Higgs; it's coupling to the total energy of the system.
You got it.
Yeah. Okay.
And that's a very GR type of thing.
It is very GR. GR stands for general relativity, and not GR, the sound that we make when we ask questions.
Right. Which, is why it goes to your field. This whole GR thing, that's your area.
Any other things about this question that feel like you want to talk about? Missing mass of the universe? Well, we could talk about dark matter if you want.
Oh, I mean, dark matter is fun. I mean, you could ask if the Higgs has anything to do with dark energy, but it's pretty clear that it doesn't. It's at best very weakly coupled to the energy field.
Yeah. So dark energy is fun. There's a difference between dark matter and dark energy, and it might have something to do with dark energy. We talk about that. Okay, so how do we know that there's dark matter? Dark matter was initially discovered and introduced as a concept when you look at galactic rotation curves, right? So. Yep. The stars on the outside of the galaxy are rotating around the middle of the galaxy because the middle of the galaxy contains a certain amount of mass. And the idea is that mass can't be accounted for if you just count up all the stars. You count up all the light glowing matter, and it's not heavy enough to allow the stars on the outside to rotate at the speed they're rotating.
You got it.
And so there's still got to be mass in it that's dark. And since then... I mean, that's an interesting thing, and a lot of people have then taken that knowledge and then guessed that maybe the laws of gravity, as we know them, are wrong. But since then
which is possible.
Well, yeah, I mean, it's always possible. But since then, we've seen a dark matter enter into physical observations in different places that aren't just galactic rotation curves, right?
That's true.
So there's the bullet cluster that we've seen where it's essentially a gravitational lensing event. Something is heavy like a galaxy, but it's dark. Light's passing through it. We can't see it. There isn't a galaxy there. In fact, what probably happened when you look at its surrounding is two galaxies collided, and then a big galaxy worth of dark matter just kind of continued floating on to the left. And so it's out adjacent to it, but it's still kind of not where...
I mean, Yeah, essentially you had two galaxies that came in, from either side, and then after the collision, there was still mass that just went through and didn't happen, but all the light-bearing stuff stayed in the middle.
Yeah.
Essentially, so it stripped the two. It stripped the dark matter from the what we call regular matter, baryonic matter.
Yeah, and so we can see that concentration of matter as in terms of gravitational lensing. So we're seeing lensing from the curvature of space-time distorting the stars behind it. And so there's that. There's a couple other places we see it in when we're trying to model galactic evolution. So we've got really big fancy computers now. Over the course of my adult life, we've developed these big fancy computers that let us look at how the galaxies have evolved and their distribution. And it looks like you can't really get the distribution of galaxies that we currently see evolving in the way we observe when we look at the night sky if we don't have dark matter essentially collapsing down first. So it looks like collapsing dark matter. If we want our models to match what we see, it looks like you need to add dark matter as an ingredient.
Absolutely. But all of this evidence is gravitational in nature.
Yeah. Well, right. Yes. Because okay. So there are third ones when we try to model the evolution of the galaxy, evolution of the universe as it expands. Dark matter has to be in there. 30% dark matter, I think.
Yep. Like 26 or something. Yeah. Very close.
So it needs to be in there, or the models don't match how the universe expands. But yeah, well, how would we talk about the dark matter if not gravitationally, Ken?
No, but exactly. That's all we can do at this point. But now we have all these big detectors that are designed to look for this, weak interaction between the dark matter and the particles that exist around us. Important detectors, like ones I used to work on.
Right, ones that are made of ice.
That's a good one.
Yeah.
Or there's ones that are made of noble gases or noble liquids. Those are good ones.
Yeah. Actually, okay, so yeah, one of the points of these question barn shows is that we can point people to the fact that in the archives of the Titanium Physicists podcast, we go through all this. Like, we did a show on detecting dark matter, right?
We did.
Yeah. So go, if you want to know more about this, go look at that. It's great. But yeah, so let's get to the overall. Let's get back to this question, because we were mentioning the dark energy, dark matter.
Oh, yeah.
Because we were saying that, okay, so it's probably the Higgs mechanism, the Higgs field coupling to various types of matter is probably what gives a lot of these types of matter, like quarks, their mass. Fine.
That's right. Fundamental particles only.
There are other ways that systems can get mass. The Higgs field itself can't be responsible for all of the mass, and the Higgs boson itself isn't a candidate as a dark matter particle, right?
That's right.
But Ken mentioned earlier dark energy, and it's interesting. Dark energy is this thing that shows up kind of like dark matter did. We have evidence that there's a missing type of gravitational matter in the universe that's fundamentally different than dark matter. Dark matter is attractive. It's like regular matter. It has mass. It pulls things towards the center. But when we model how the universe is expanding, there's another term in that model. The universe requires an additional term that causes the universe to expand, right?
Yeah, absolutely.
That's called dark energy. And we actually, our first show, we talked about one candidate for dark energy called phantom energy that might cause a big rip. But there's a variety of different types of matter that might be causing this weird gravitational repulsion, because the universe definitely is accelerating in its expansion. And so it's interesting because the Higgs might show up again, right? We're not sure what kind of matter is causing gravitational repulsion, but one candidate for it, and I think we've done a show on this one too, one candidate for it is it's called vacuum energy, right?
Oh, yeah.
So vacuum energy acts like something else called a cosmological constant. It has the capacity to cause gravitational repulsion on very, very, very large scales. And so it's possible, among other possibilities, that the Higgs field is somehow at really large scales. The lack of the vacuum energy, the vacuum state of the Higgs field might be causing the universe to expand. We're not quite sure at that level. Things become fairly speculative because, taking in data at this level is pretty new. We're still dealing with very large scales of time.
Very difficult.
Yeah. So, I mean, we'll know in the future, maybe.
Wasn't the cosmological constant what Einstein called his greatest mistake?
He did. You know the story of that, right?
I don't. I just know that he said that.
It's really funny. So first he came up, he and other people, Friedman, Robertson, no, not Friedman.
Let me guess, Walker?
Yeah. Friedland, and Lemaitre. Right. So there were four people working on this problem, essentially, working on these types of solutions from the late 19-teens to the late 1920s. And the first and simplest solutions that you can come up with describing how the universe behaves at very, very large scales is one that causes the universe to increase in size or decrease in size. The size of the universe is dynamic. So things might come out of a big bang. They might fall back into a big crunch. They're not quite sure. But Einstein saw that result and was like, no, that's not possible. Not right.
Nice.
And then, so it's like, well, okay, Einstein, I mean, I guess it's your theory. So he added by hand an extra term into the equation called the cosmological constant. Because if you add in this other term, you can make something called the steady state universe, which is a universe whose size doesn't change, stays the same forever. And it's an interesting model because he was like, there, we've got it. And then as soon as he did, Hubble released his results that say, hey, we found out that the universe is increasing in size. The universe is expanding. And he was like, oh no, my biggest mistake. But it's ironic that he added this term because later he did it by hand because he wanted this. It's the simplest way to make a steady state universe mathematically. But since then, other mathematicians have looked at his work. There was a guy called Lovelock. They've looked at this work and they said, actually, if you want to be mathematically precise, you know in calculus how sometimes when you're doing an integral you have to add a little constant in the end plus c. Yeah, essentially you have to do something similar when you're writing out the equations for general relativity. So for all generality's sake, you should have a cosmological constant in your general relativity equations. So Einstein added it by hand. He immediately regretted it because it looked like he had added it just to disprove something, just to allow for the possibility of something that's clearly not true, right? I mean, Hubble discovered the universe was expanding. Boom, you don't need a steady state universe. That said, it looks like it was okay. It was mathematically kosher to add a constant there, and that for all generality's sake, there should be a constant in the equation. And then it looks like this cosmological constant is one of the candidates for dark energy. So Einstein's greatest blunder might have also been his most prescient success.
But surely, obviously the universe could expand at different rates. Do you have to fine-tune the cosmological constant to have it expand at the rate that we see?
Yes.
Or does it have some basis in some kind of fundamental, numbers?
Yeah. So there's a little bit of both on this. It might be that it's just a fundamental number, like pi. It describes the just fundamental curvature of the nature of space-time.
Right.
So instead of saying that space-time is made of bricks that are flat, you're saying space-time is made of bricks that have a little bit of curvature to them. That said, it is something that we have to fit for. We don't know its value, but we do fit for its value when we're looking at describing the universe as an accelerated expansion. So it is a number that we fit for. It's called the Lambda cold dark matter model. Lambda is the cosmological constant, and yeah, it's entirely possible. So it is a number that we experimentally verify. And in the Lambda cold dark matter model, what we're saying is that the dark energy is this cosmological constant term. That said, people think that maybe it's possible that the cosmological constant, this effect that we measure, is generated by matter fields, that it's not a fundamental building block of nature. It's not fundamental to the bricks of space-time, but rather that it comes about from vacuum energies of different fields, because when you look at how they should gravitate, it looks like they should gravitate like a cosmological constant. But there's a big embarrassment here, right? So for the first time, somebody said, "Hey, look, we can make cosmological constant vacuum energy by looking at the vacuum energy of different fields. Finally, everything is, we've unified this. We know how fields gravitate." But when you do that calculation, you're off by 120 orders of magnitude, I think.
Oh, is that all?
Yeah. I mean, it's one of the biggest embarrassments because the cosmological constant that we measure in the universe is actually very, very small. Whereas the cosmological constant predicted by the vacuum energy would have to be fairly large. Actually, formally, it would be infinite, and so people have to put in little cutoffs. So they say, well, what if the past the Planck's length, you can't have any vacuum energy, and so they put in kind of arbitrary things. I mean, you can argue about whether they're good or not, but the result is 120 orders of magnitude. It's huge. The difference between what we've measured and what we predicted is huge. So there's still a big hole in the theory as to what's causing the cosmological constant, how we interpret it.
Well, that is interesting. Not exactly the topic of the question, but very interesting.
Yeah. Well, it might be the Higgs field, the vacuum energy of the Higgs field, contributing to the expansion of the universe. This cosmological constant. We don't know. Well done. You tied it up in a nice little bow there. Yeah. All right. Well, I think that's it for this week's Question Barn. Thank you, Ken. Thank you, everybody else. Thank you, Ralph, for asking a question. Anybody else, if you want to ask your question to Question Barn, send them in at TIPHYTER, typefighter, at titaniumphysics.com, and we'll have an answer for you. I'm trying to get the next episode of Titanium Physicist proper out as soon as I can, but I'm working on it. Life's busy. Okay. See you, everybody.